There are a lot of do's and don'ts that I'm going to highlight for the strategy on the retrosynthesis. Please keep in mind them, because sometimes starting from the wrong part of the molecule, starting from the wrong foot on retrosynthesis, it puts you off completely. This is one of the reasons why sometimes I don't want to give you starting materials. Because you think, okay, I have to use the starting materials, but you use it in the wrong way. You focus, you obsess of using that starting materials in that way, forgetting that you could have used it another way. Or maybe you don't use it at all. In my case, when I suggest a starting material, normally is a suggestion. If you don't use it, you don't lose marks. As long as you put something plausible, you solve the exercise anyway. I don't mind. For me, retrosynthesis have to be creative. Today we'll start with some, if you watch the video, it's gonna be long because there is a lot of stuff to do, but it's gonna be hopefully easy. So again, I always like to consider retrosynthesis like, forget about the history of retrosynthesis. We don't have time to do that, and it's not that useful. Consider retrosynthesis from the creative point of view. Yes, you want to be very, very methodical, and you're retrosynthesis. So if you learn how to do certain things, you see, you spot a functional group, and you say, okay, I know where to start. Have a good look at the molecule, and you should imagine already, because hopefully you practice quite a lot, and you should know already where to start. But again, intuition is great. Let's forget about emotions, especially speed pipe, because I don't think you can use speed to retrosynthesis. But yet, this is the part of the brain that works on that. This is what I call the creativity part. So even if you see a pattern, but you end up doing a much longer retrosynthesis than one that I was telling you before, carbonyl on, carbonyl off. That's nothing wrong. But if you see something more elegant, something like symmetry, something like a functional group that if I use that at a specific moment, it actually saves me 2 steps. This is what you want to do in the lab. Because the more step you have in the lab, the lower the overall yields, or the more complicated the reactions become, or the more byproducts you need to separate from one from the other. So if you can see, if you can be creative and can spot maybe a central part of a molecule, which helps you. If I do that now, I start from symmetrical starting material. So maybe I do the same reaction twice in one pot. That's great. Okay. How do we play with functional groups? There are two possible ways to think about it. Either you think about from the keys of a piano. Each functional group can be put like something like in a linear way, one after the other. I prefer to use it as a chess, like the chess game. So in the chess, the very important part of the chess game is that you never think in a linear way with one molecule, one move after the other. You always have to move to think about 2, 3 moves and anticipating the possible problems that may come from the reaction for your opponent. So this is why I really, really like to connect retrosynthesis with chess, because you always need to think about, especially if the molecule is large, you need to think about 2 or 3 steps in advance. So you put a functional group, you say, okay, that's an easy start. But when I do the synthesis, that influences the other part and the other part of the molecule. So cancer to start from another place. So think about the potential problems. Symptoms. This is something that we did last year, but we're going to do it first now. I really hope that with all the retrosynthesis that we mentioned between myself and Marcella, you know now that eventually one of the big do in retrosynthesis is whatever R and R1 is, if you cut here, you have to end up with R minus and R plus, or let's say R plus and R prime minus. moving the charges, separating the charges is the most important thing in retrosynthesis, but this is the most, I'm not gonna lie, it's the most important thing in chemistry. Whatever you're doing, it doesn't matter if it's organic chemistry, inorganic chemistry, physical chemistry. If you want to create a bond, and if you think from the retrosynthesis point of view, so what starting materials do I use to create that bond? You have to separate the charges. You need to have a nucleophile and an electrophile. If you spot a good nucleophile and a good electrophile in your reactor, you already found that bond. Then you need to think about, if I use that nucleophile and that electrophile, will affect the rest of the molecule? If the answer is yes, cancel and start from something different. Or prevent it. Think about the use of rotating groups. We did that last year. If you have two different sites that might react in the same molecule, you might think that in one of the starting materials, you use a rotating group. So from the strategic point of view for the exam, remember that you need to tell me about the protecting group only in the forward synthesis. I don't care. I don't want you to tell me, yeah, I need a protecting group in the retrosynthesis. The retrosynthesis, you basically chop off the carbon bonds or the carbon heteroatom bonds the way they are. But if there are potential regioselectivity or chemoselectivity problems, you want to add the protecting group, potential protecting group in the forward synthesis. Remember something else. Protecting groups are necessary evil sometimes. But if you avoid using a protecting group, it's better. Because if you are in the lab, if you're on the paper, you don't care. Protecting group on and off. In the lab, remember two things. Removing protecting groups and putting protecting groups is not always as easy as it seems. And you're always ending up in having two more steps. The yields on those are always not, in theory, they should be 100% in placing it, 100% in removing it. It doesn't happen very often. I think you saw by now the retrosynthesis is never a very, I'm sorry, I'm going to say it's never a very clean chemistry. There are so many things that can go wrong. But if you avoid using protecting groups, also, if you show me, you can avoid using protecting groups also in the retrosynthesis and forward synthesis, I appreciate. So symptoms, again, let's start this. Put the charges in a plausible way. For instance, if you have this one, always try to, if you can, always start from carbon heteroatom bonds. So start chopping off groups, separating two parts of the molecules, starting from a carbon heteroatom. Be careful unless the carbon is next to an aromatic, is part of an aromatic ring. You don't want to do nucleophilic aromatic substitution unless it's really necessary. We will see with more examples. So in this case, you put a plus here and a minus there. Remember that the symptoms are great to figure out the separation of the charges and the potential new bond that is forming during forward synthesis. But they are not chemicals. You need to tell me what the chemicals are. So if you want a plus here, next to carbonyl, you must have a living group. So this carbon, whatever else bond, then whatever else has to be a good living group. Because if you don't have a good living group, and again, this is chemistry from the first, that we start from the first year. If you don't have a good living group, if you attack the carbonyl, you end up with the alcohol, not with the carbonyl again. Only with a good living group. This one attacks, breaks the carbonyl, tetrahedral intermediate, and goes back to carbonyl, kicking out the living group. Only in this case. That is true in theory, that is true in practice. I will not ask you for mechanisms in retrosynthesis, any mechanism. If you can do the mechanism, also the exam, please do it. You don't get marked down because you do mechanism. You will never be marked down if you do a mechanism with me. But you're not supposed to do it. So if you don't want to do it, don't do it. Choose very carefully your potential reagents And also the choice of the potential reagent has to be plausible with the rest of the molecule, because now we are focused on the bonds. But let's say that either on this side or on the other side, there are groups or other functional groups which are affected by the conditions you're using. You need to think about that too. That's why I keep saying the chess game is probably the best. In this case, you can start from an acid chloride, you can start from a carboxylic acid itself, just using strong acidic conditions, which turns this one into protonated water, which becomes a good living group. Normally, I would suggest you to start from acid chloride. Halogens are the best living group ever. You can be creative and start from anhydride, it doesn't really matter, as long as it's plausible. Okay, but in this case, if you put the plus here, you want to restore the carbonyl. You must have a good living group. And this one is an alkoxide. Normally you don't want to use the alcohol as it is, unless the electrophile, this one will be your nucleophile, unless the electrophile is going to be super activated. Sometimes you want to do, the alcohol itself is not that nucleophilic, and sometimes you want to use a base and use the alkoxide instead. But again, think about it, because if you're using a base to create the alkoxide, you're in basic conditions. Don't then tell me that in the same step I use a protonation of something. This is again something that you need to think about 1, 2, 3 moves in advance. I used this one last year, or the second year, to play with synchrons. I'm not going to do that again, all of it, because we never have time to do them all. But if you cut here, we're going to see the systematic formation of certain functional groups. You have a double bond, normally double bond starts from, if you have a double bond, you may think it starts from an elimination, normally elimination of water. It could be an elimination of halogen, but normally it's very likely that you're going to use, again, carbonyl chemistry, attack on something which carbonyl doesn't have a living group. It creates the alcohol. Remember the magic word, if you can conjugate with something, that double bond is so much easier to form. If it conjugates with another double bond, or even better, with a series of double bonds, like an aromatic group, that the elimination is very easy. In this case, if you form it, it's conjugating with a carbonyl. It's a good double bond. It's a good carbon-oxygen double bond. And in that case, the elimination is going to be much easier. So you can start from A. You can remember whatever you did with John last year as well. Kinetic, and we did it in the lab this year with me and Marcello. Kinetic or thermodynamic conditions. So if you have 2 possible alpha protons that you can remove, think about what you did in practice. If you want to do the reaction selectively here, you need to use kinetic conditions. So very low temperature, very bulky and basic base, something like LTA, something that takes immediately the protons which are more accessible, and it doesn't go towards the thermodynamic part. So for the formation of the most stable double bond. So in this case, for instance, in the forward synthesis, you need to tell me exactly these conditions. Think about the nucleophile. If you have alpha protons, that's the best nucleophile. It's a soft nucleophile. It doesn't attack the carbonyl. You can use it easily. It doesn't necessarily attack the carbonyl. The electrophile, the other symptom, might count for, you must put a plus here. Plus here means that one of the carbons here is very electrophilic. One of the easiest way, again, you're going to see it very often. One of the easiest electrophilic carbons is when it is a carbonyl. In this case, you don't have a good living group. You found the alcohol, but you know that the alcohol is going to be sacrificed to form your double bond. That one, you can call it an FGI, functional group interconversion, or you can call this one a sacrificial group. Both of them are good to me. The most important thing is that you want to go selectively to your product. So for instance, if you invert the charges, like you do here, which is still plausible on a paper, you cut on carbon-carbon bond, you put one minus on one side, one plus on the other. Try to do them both. Especially when you do the synthesis, if you want to do the synthesis here, you say that, yes, this one could be a Grignard. You need a very strong delta minus here. So the easiest way could be an organolithium or a Grignard. But the organolithium or the Grignard are hard nucleophiles and hard bases. Instead of doing the SN1 that you would like to do here, the SN2 that you would like to do here, you might attack the carbon instead. Plus, in this case, even if you would, let's say that you use a Gilman reagent. Let's say that you are creative. Let's say, if you remember how to use the Grignard, if you want to turn a Grignard from a hard nucleophile to a soft nucleophile, you can say, I do the Gilman. You mix your Grignard with copper salt. You create a double distribution of the charges. It becomes a soft nucleophile. You can do 1,4, or you can do an SN2 instead of the net attack on the carbon. So if you tell me, yes, I will use the Grignard here, because I've used the Grignard into the Gilman reagent, and I can do that. There is another problem. Once you do that, here, you need to dehydrogenate to form your double bond. You can form the double bonds with dehydrogenation of saturated compounds, but it's far more difficult. So here we have several problems. So you choose, once you cut and you put the charges, you should immediately click that this one, the first pathway, is the best one. It's all about strategy, because the chemistry is nothing new to you. The chemistry you're using is nothing new to you. This is the typical example of wax on, wax off, carbonyl. If you want to do this kind of compounds and you have a saturated, whenever you see saturated aliphatic, you can, if it helps, always expand it and put all the protons that are missing. If you have something like that, you can always think about that. You start from a carbonyl and you do. Do you remember reactions that turn the carbonyl into an aliphatic, a saturated one? Does anybody remember any? In this case, if you just tell me at the exam, I use that, they'll do to me. There are three, actually. One of the easiest one is probably, if you cannot hydrogenate easily anything else, you can just use hydrogen with palladium over carbon. Typical hydrogenation, and they will do. But in a lab, you need to have cylinder of hydrogen, and believe me, health and safety is not very happy with you having a cylinder of hydrogen. But you can do something simpler. Do you remember two names? There is something that you need to remember in each. I know that I like to play with the brain when you do retrosynthesis, but sometimes remembering some of the names are good. In this case, there are two typical reactions. Wolff-Kirchner in basic conditions, or Clemensen in acidic conditions. In this case, you can turn this one in synthesis, you're going to do this reaction. So it doesn't matter, in this case, it doesn't matter if you're doing hydrogenation proper. Remember that in the lab, you wouldn't do it, but if you tell me on a paper, on an exam, I will definitely accept it. I don't care. They're not in the lab, they're on exam. So if there is nothing else that can be affected by the hydrogenation, just tell me hydrogenation with palladium over carbon, because you definitely need a catalyst. and I will do. But if you just tell me I will do Wolff-Kishner, remember that you're doing basic conditions. I will not ask you the perfect conditions of the Wolff-Kishner, reagents of the Wolff-Kishner on the forward synthesis. But you need to imply, you're implying using the Wolff-Kishner that you have to do it in a basic conditions. If those basic conditions affect the rest of the molecule, because you have in the other side of the molecule a basic labile compound, then you do the Clemmensen instead, or the other way around. From the strategy point of view, if you want to use a carbonate, because doing this reaction is so much easier than trying to do a Friedel-Crafts alkylation, because that will be the other option. You cut here, you do straight away a Friedel-Crafts alkylation. I will accept it in this case. It's absolutely fine. I prefer to use the carbonate because it's so much easier. The Friedel-Crafts acylation is immensely easier than a Friedel-Crafts alkylation in the lab. Then you need to tell me how to remove the carbonyl. And if you tell me Wolff-Kishner or Clemmensen, and you don't care at all about the basic on acidic conditions, they are equally good. If the rest of the molecule, let's say they have something else on this side or on this other side, and you have something which is affected by other basic or acidic conditions, you choose one or the other. Sometimes I ask you to go back till benzene. We saw that last year. It's very unlikely that I'm going to ask you in the third year. In the second year, it was just to state that this reaction might work. So even if you want to use anisole is incredibly cheap and a commercially available compound. If you are in the lab, you will buy it. You will never produce it from benzene. It's long, time consuming, expensive, and stupid. Because why would you do that? But if you're on the paper, sometimes if I ask you, please do the retrosynthesis up to benzene as a starting material, this is all chemistry you know already. We start with the benzene, with the nitration, reduction of the nitro group to an amino group. I would like to emphasize that this whole part is an FGI, because eventually you get rid of all of them. Or you can call it a sacrificial group, like we were saying before for the alcohol. You go from the diazole, then you use a methoxide, sodium methoxide, potassium methoxide, and you can easily get methoxybenzene or anisole. But you can get it easier from a Sigma Aldrich catalog. For I would say no price, but it's much cheaper than others. I will not say too much on this one this morning because we will do 1.3 and 1.4 and 1.5, but also the 1.2 actually, dicarbonyl reaction later on in this part of the course, because I want to do them again to keep using the carbonyl chemistry in the best possible way. Let's see that very quickly. Carbonyl chemistry, again, is super versatile. But again, for all parts of retrosynthesis, when you cut either here or there, in this case, it's symmetrical, you don't care much. But you must identify on your symptoms a nucleophile and an electrophile. In this case, again, it's symmetrical, basically the self-condensation facet but of the aldehyde actually. But what if is in this kind of reaction? Is it kind of compound? Have two possible pathways, A and B. So once you disconnect on a carbon-carbon bond, again, the drill is always the same. One positive charge, one negative charge. Then you need to decide what is the reagent that creates the positive charge or the negative charge in each side. So the blue A, you can cut it here. You can start with this compound. Is it likely? Is it doable? I will say yes, it is doable. This one, if you cut here and you put the positive charge where normally wants to be between a carbon and a carbonyl, the positive charge wants to be on the carbonyl because it's naturally the electrophilic part. So automatically you need to put the negative charge here. The negative charge on these carbonyl compounds can always come from the abstraction of an alpha proton. That's doable. So this reaction is absolutely plausible. Okay. In the lab, there are potential problems. This one is also plausible. You cut here, and again, you have another carbonyl on the other side. So again, you can put a positive charge on the carbonyl, and here you have the starting materials. You can imagine, in the starting material, you can imagine automatically alpha protons. Again, doable, absolutely doable. Here you have a positive charge. Here you have a negative with this ester group pending. What's the difference between these two reactions? Potential reactions. This one has a potential problem of let's say chemoselectivity. Can go one carbon or the other. In this case, it doesn't really matter because it's symmetrical. The other potential problem is that here you need to have a living group, but also this one is a living group. That makes one compound like that with two living groups makes this carbon of the carbonyl very, very electrophilic and very, very unstable. Remember that the most reactive compounds are also the most unstable. And the most unstable compounds also give you a bunch of side reactions that you do not expect sometimes. On this one instead, what could be a good living group? It could be an halogen, absolutely. But remember what we said at the beginning. What if you want to play with the symmetry and with economy of your reaction? Can you see another living group that actually makes this reaction so much easier? The ethyl side. So basically the same compound. You put in base the same compound and it self-reacts. So this is the self-reaction of this compound. If you can do that, it's great. But if you're at the exam and you want to put a halogen, it's good with me. Absolutely good. You won't get extra marks because you got for that one. But if you learn how to do this one, it's better. This one, again, I will accept it. There's nothing wrong. If you are in the lab, the reaction will be more problematic. But at the exam, this is the typical reaction that both answers are good to me. If you explain everything at the exam, you will get full marks no matter which one. 1,4, quickly. If you cut on the 1,4, which we will see is what we call one of those illogical ones, you must have one side of they look the same, the symptoms, but one has a negative charge, one has a positive. One exploits the alpha protons. The other one must have another living group next to the carbon, because if you want to have a positive charge on that carbon, you must have a delta minus on the other side, which is also a living group. Again, probably the easiest one you can use is a halogen. There are others, but an halogen is always good with me. Remember also another thing, that sometimes this is part of a molecule, so you also have to place the halogen. So you need to know how to make halogenoalkanes as well. We will say that too. So from retrosynthesis, if you have 1,4, you cut normally between carbon 2 and 3. You separate the charges. I will suggest in this case, again, you can put the minus here and the positive one here. You can have the positive one here and have a halogen. But first, this one is going to be more difficult to synthesize if you have halogen there. Plus, this one, in this way, the cyclohexanol, whenever you take a proton, an alpha proton is symmetrical, so I won't create any chemoselectivity, retroselectivity problems. So again, thinking ahead. For synthesis, you might need to activate the carbonyl. Remember, you did all this stuff with Joule as well. Activation or taming the enolase. Sometimes you have to do either one or the other. In this case, it's activation of the carbonyl. The carbonyl itself, sometimes if you want to block the enolate, one of the easiest way is to create an enamine. You react with a saturated, and we did that in the second year as well. You can activate the carbonyl either protonating it or by doing one of these reactions. Again, you do this if, for instance, the protonation, which requires acidic conditions, might affect the other side of the molecule. But typical example, it could also work that you just use a cyclohexanol and you take a base, you use a base, it takes an alpha proton, and then the alpha proton reacts to the other side of the molecule. What's the problem, the potential problem of using a base with the cyclohexanol, which is prevented if you do that? You did that with Joule several times. What's the problem of the cyclohexanol and a base? Anybody remembers what happens? You put the cyclohexanol, you use a base, whatever the base is. You take one of the alpha protons. What can happen instead of reacting with your compound? Not necessarily, no. It's not that. That is not the problem. The main problem of that one is potential self-condensation. So this one reacts with another molecule. As soon as you take out one of the alpha protons, it might react with a molecule which is neutral. So where you didn't take the alpha proton yet. Self-condensation of ketones, in this case, is something very usual. You did that with Joule, you did that, potentially you did that in the lab where we did the kinetic and thermodynamic, because we block the enolate. If you want to block the enolate, is to prevent also self-condensation. In this case, you block it with this enamine. This enamine can react with your compound. What you want to see is here. Again, I will not ask you for the mechanism, but if you do know the mechanism, it helps. Again, first year reaction. This is an SN2, a simple SN2. Then, of course, you need to remove that big, bulky, saturated heterocycle by a simple diluted acid conditions, hydrolyzation, and then you have your 1,4. Okay. So, message to take home here. Cut here to the negative charge. Think about that these R groups, R and R prime, can be completely different side of the molecule. So think about which one is the best to put, where to put negative or the positive charge. That's also strategy. But at the moment, we just care about doing the forward synthesis in the best possible way. This is just, I will leave you this one for home. This is just how do you do the hydrolysis from the mechanism point of view, but we don't focus on that today. Group disconnections, again, 1,5 dicarbonyls is another one of that when you exploit the proper nature of the carbonyl compounds. In this case, we're gonna see that. I will not stay too long because we're gonna do that specifically in one of these parts, okay? Before now and the end of the course. But 1,5 dicarbonyls normally, if you see carbonyls in 1,5 position, think about alpha beta unsaturated carbonyls. One of those has to be an alpha beta. So one of your starting materials might have an alpha beta unsaturated carbonyl. Because you put, again, as usual, negative charge and positive charge on one side, but this positive charge, if you do the typical charges, delta minus, delta plus, delta minus, delta plus, This one can do conjugate attack. So in this case, with the 1,5, if you want to remember, you use the conjugate attack. If you don't want to remember, because this is nothing that you must remember, root learn anything, you put the delta minus, delta pluses, delta minus. The only thing you really need to remember is that your nucleophile to do conjugated attack has to be soft. If you want to do conjugate attack, the nucleophile always has to be soft. Otherwise, it will attack the carbonyl. If you have anything which has strong delta minus or a proper negative charge next to carbon, let's say a Grignard reagent will attack the carbonyl instead. So these are the typical condition for the 1,5. Again, don't worry if I'm going fast now because I want to do alcohols and amines in the second part of the lecture. And we are going to do this one more specifically, more in detail later on. But again, this is just how to split the charges. If you have two potential positions on the 1,5, they are probably most likely equally good. Again, you just need to think about what is this R group and what is this R prime group. If you want to create your alpha beta unsaturated in an easy way, look at what is the rest of the molecule that you need to cut. If that links to the formation of the alpha beta unsaturated, you probably want to do the alpha beta unsaturated here. Otherwise, if it's true the opposite, you will do on the other side. But potentially speaking, they are equally good. We don't care. There is not one right and one wrong. There's only sometimes one easier and one more difficult way. But they're, on the paper especially, they're equally good. A very quick suggestion from the strategy point of view at the exam. If you start with something, you identify one or few parts that you want to disconnect. Trying to do the retrosynthesis, the synthesis, at least attempt the synthesis as soon as possible. If you even think that this is going to be problematic, cancel and start from another side of the molecule. If instead you say, okay, in this part, if I cut here, I have the double bond, the alpha beta saturated on the other side. Will the synthesis of the alpha beta saturated on the other side be easy or not? If it's easy, I'll carry on this way. Not easy. What if I try the other way, straight away, without thinking about all the rest of the molecule? I've seen too many times, I'm telling you because I've seen too many times people get stuck. I open an exam paper and I see that the first reaction was plausible, but then the student didn't know how to carry on. If you don't know how to carry on, try, maybe it's not the most intuitive part. So try to cancel and go from the other side. Radioselectivity and stereoselectivity problems. Radioselectivity is when you have two potential attacks. Let's say, like we just seen before, you have one alpha beta unsaturated compound, and you can, depending on the nucleophile you're going to use, you can have either the attack on the conjugate, so on the 1,4, on the ending part of the double bond, or you can have direct attack. That's a potential radioselectivity problem. How do you solve radioselectivity problems? Normally, with the right choice of reagents. You want to have 1,4 attack or conjugate attack. Even if you want to use the Grignard, we saw that before, you might turn it into the Gilman. You create your Grignard, but you say, yeah, but I add copper salt, and in this case, it will go 1,4 instead of 1,2, or conjugated instead of direct attack to the carbonyl. That's great. Maybe there is another way, a simpler way to do it. But if you do that, you're not wrong. You can do it. Remember reactions that sometimes are reversible. And especially remember this part. This is just what we talked about. If you have a hard Grignard reagent or organolithium, and you say I do conjugate attack, it's going to be a no. If instead you have a soft reagent, something like an alpha, you have two possibilities to do conjugate attack and a carbonyl attack. Let's say on you have this molecule, and you have on the other side potential enolizable compound. That's a soft nucleophile. If you tell me that it does that, it will be wrong. That won't work. This one will always do that, and that. Okay. Strategy. And here, sometimes radioselectivity, it's instead of playing with the right reagents, you sometimes solve the problem by using activating groups. Using activating groups is something that you don't see immediately. But when you do the synthesis and you recognize this is a potential radioselectivity problem because you have this compound, you have 3 alpha protons here, alpha protons there. Yes, you can say, and you have to say on the forward synthesis, if you want to use that, you can say, I use kinetic conditions or thermodynamic conditions. So you did that in the lab. Let's say LDA minus 78 favors kinetics or favors the attack here. The LDA takes one of these protons more likely than it takes one of those. If instead you want to attack here preferentially, you use higher temperature, and like you did in the lab, you use triethylamine, a much milder base. But sometimes it's easier to do activating groups. So if you really want to attack here, remember what you saw in practice in the lab. If you remember from the NMR, most of you must remember that the thermodynamic product was always contaminated by a little bit of the kinetic one. That is normal. That is easy to happen. What is not easy is sometimes to separate the two products. If you want to prevent it completely, this proton, if you put this one, which is going to be an FGI, or you can see it as a sacrificial group, you put an extra carbonyl in between. This proton now is far more acidic than any of those. You are activating these conditions 100%. In this case, you won't have any traces of kinetic product. So you start from this reagent instead, carry on your reaction, you use a base, now you're selectively extracting only this proton. You can do your SN2 easily. And then, do you remember at all how to remove? There is something that you saw already, some of you at least must have had this reaction on the presentation of the second year when Joel did the carbonyl, this part of the carbonyl chemistry. If you want to have your target molecule, now you have to remove this one. You remember how to do it. Which is a reaction that only works if you have another carbonyl, if you have two this carbonyl. One is in alpha beta. Only this case works. You need to do, if you want to remove this group, you need to decarboxylate it. There are two ways to decarboxylate it. Either you hydrolyze the ester and you heat it up massively, or you can use the chloride, will be lithium chloride or sodium chloride, in the DMSO, and it will decarboxylate straight away. I think this reaction is called capture, if you want to remember the name. But you don't need to remember the name. You just need to remember that if you have basically an ester group in 1, 2, 3 position, in position 3, you can decarboxylate it straight away with lithium chloride in DMSO. And that will help this reaction. So you can think about activating with this extra carbonyl, because then eventually you will remove it. And this reaction is is one of these reactions which is very efficient. So you don't have problems in the lab of neither selectivity nor yields. So you're actually, yes, you're adding extra step, extra energy, extra solvent, yes, but activating groups like rotating groups are necessary evil sometimes. Then you can do this reaction, how to include your, if you want to know also how to include your activating group, because you don't start from this one, you start from this one activated already. So at some point you have to put it. This is just an aldol condensation. This is one of the simplest aldol condensations that you can ever have. And again, aldol condensations are reactions that we started using from the first year. Chemoselectivity, if instead the problem where you have two similar reactive functional groups, and you can choose one or the other. For instance, a typical example is two different carbonyls. We saw that when we started using protecting groups. If you have two carbonyls, and let's say you want to do a nucleophilic attack on this carbonyl selectively, you have to protect this one, because the carbonyl of the aldehyde is more electrophilic than the carbonyl of the ketone. So if you put a nucleophile now, it will attack the carbonyl of the aldehyde. That's why if you put a protecting group of a carbonyl now, it will selectively protect only the carbonyl of the aldehyde. So if you want to have this one, for instance, which if you can cut here, you can immediately think that you might start from a Grignard reagent because you form an alcohol. You need to know that the aldehyde will be attacked first. So what you do instead is protection of that carbonyl, which can be selected for the same reason, because it protects first the most electrophilic carbonyl. Then you do your Grignard attack on the unprotected carbonyl, and then you remove your protecting group in acidic conditions. Let's be careful, because sometimes the acidic conditions also remove the alcohol, because formation of alcohol is the easiest way to put double bonds. Sometimes it's possible to functionalize one group instead of the other. It's not very intuitive from here now, but we will see with it how we carry on. Remember, this is something that, again, we're going to see with the amines, we're going to see with the rest of the strategy of this part of the course. Always try to, a good way to start a retrosynthesis is by cutting carbon heteroatoms bonds, unless you want to cut these carbon heteroatom bonds. If you cut here, you're implying you're doing nucleophilic aromatic substitution, because if you're cutting here, the nitrogen is almost a nucleophile. And if the nitrogen is the nucleophile, you put a delta minus on the nitrogen, you must put a delta plus on your benzene ring. And benzene rings like to be nucleophilic, not electrophilic. It does happen. There are tricks that we can use, diazono salts. We can activate in other possible ways. But if you can do something else, something like cutting from here and keeping this nitroaniline, that's easier. That's a lot easier. Don't try not to cut carbon heteroatom bonds if the carbon is part of an aromatic group, because the heteroatom is normally the most nucleophilic part. In this case, the chemoselectivity problem is when you have to do this reaction in forward synthesis. Sometimes you get away with that, but you need to know, if you do that, you need to know exactly what reagents you're going to use, because if you have this dinitrobenzene, which can be easily formed, because the first nitro on a benzene gets easily, the second nitro gets more difficult, but it goes in meta. So this one is easy to form. But then you need to reduce one of those selectively, only one of those. No matter which one, but only one of those. And in this case, you get away with that because if you use this sulfur compound, you can smother the reaction. And as soon as you start reducing one, this reagent is not powerful enough to carry on the reaction and reduce also the other one. If you use any other typical reagents that you use to reduce nitro groups, there's a huge amount of you might have a huge amount of dye reduced. So diamino instead of keeping this nitro. It's always likely. So either you know exactly the condition that you're going to use to selectively, in this case, reduce only one group, start from another point on your reaction. Try to use something different. In this case, this reaction works well enough, but sometimes you're not that lucky. Sometimes if you do this kind of reactions, for instance, you want to create this compound, if you think about cutting there, this one is phosgene. Apart from being extremely toxic, and nobody wants you to use phosgene in the lab, this one is extremely toxic. This reaction will always produce double. This dichloro is basically this one. Look at that. We always say that if you want to make a carbonyl more reactive and you want to have a good living group, you start from the halogen, so from the acid chloride. This one is a di-acid chloride. This one attacks anything. And when you mean anything, is including your DNA. Easy as that. So this reaction's phosgene is extremely toxic. Plus, your reaction is not going to be selective. It's very, very difficult. Even if you add exactly 1-to-1 equivalent, you will end up having half equivalent of this one and lots of starting material from reactor. You can decide to go for, on the paper, to go for something which is far more reactive on one side, but this compound is as toxic as the phosgene. So again, remember when you need to use cyanides, sodium cyanides, potassium cyanides, phosgene, and at the exam, please do it. I don't care. I don't care if it's toxic or not. I'm just telling you that if you find another way, yes, on the paper you'll get full marks. On the lab, you'll get a no. Sometimes it's very, very difficult. I don't want to stay too long on this one because I'm already late on that. But for home, think about how to do this reaction potentially, avoiding this part. Because if you want to make this molecule and you think about using again one equivalent of each, you will end up with mixtures which are the boiling points of these compounds are so close that separating them is awfully difficult. It is possible, yes, but it's very, very difficult. Again, this is the reaction that you're going to do at home. There are so many other exercises. I want to stop here for the moment. There are so many other exercises that I'm going to give you in the slide that are already in the slide for home. We'll do a quick break. I will share now my second part of the slides, which I think is one. So let's start with alkyl phenamine. Hide. So let's start with the alcohol. How would you make this one? Quick as that. If I tell you number of carbons starting from 1, 2, 3, let's say, because it's more difficult Well, we will play with the saturated, with the aliphatic chains, but later on, and it's not as important now. Where do you cut? What would you do? You need to get a alcohol. There are several, we discussed that already. We discussed that in the past. There are several possibilities to get a alcohol in that position. What do you think is the easiest one? Where do you disconnect it? Think about the carbonyls. If you want the alcohol, after you add your nucleophile, none of those must be living groups. If you want to keep the alcohol using, let's say, a Grignard reagent, which is one of the most common one to get alcohol, if you want to keep the alcohol, you must not have living groups, because the carbon double bond oxygen is more stable than the carbon single bond oxygen. If there is a chance to restore the carbonyl, it will do it. If there is a living group, is the driving force to restoring the carbonyl. If you don't want that, you must have, I don't know, CHs, whatever, or let's say if it's a aldehyde, again, you will never have restoration of the carbonyl. That's very important, because in this case, you really want to keep the alcohol. So for instance, you can cut here. You can have a Grignard reagent, which is your good nucleophile, very strong, likes to attack direct carbonyl, which in this case doesn't really matter because you can only attack the carbonyl. There is no possibility of doing 1,4, for instance. But if there was 1,4, then you start thinking about, what do I need? In this case, you clearly attack your carbonyl here. This one goes up. You formed your alkoxide because you're in strong basic conditions. So in your forward synthesis, in this case, you also need to tell me I will use something which provides the proton for the alcohol, okay? These are the conditions that I need you also to keep in mind when you do forward synthesis. That's the easiest way to form an alcohol. On the synthesis, you form your Grignard, you form your alcohol, you tell me that you also need water. What about this one? This is a more difficult one. Let's say that we're counting from 1, 2, 3, 4, 5. You have this alcohol here. So technically speaking, you can cut if you want to have the same way. If you want to do the same way as the reaction before, again, separation of charges, minus on one side, plus on the other side. If the plus is this carbon, because you imagine getting an alcohol from a direct attack on the carbonyl, which doesn't have a living group, so it leaves the alcohol nicely. If you have this plus here, you can cut 3, 4, or 4, 5. Here comes the strategy. Where do you want to cut? What do you think is best? 3, 4, or 4, 5? Any of those, if you put the plus on the carbon, former carbonyl, it's good. Technically speaking, they're both good. They're equally good. One of them is better than the other. And that depends on the other side of the moon. Which one you think? My suggestion, whenever we're doing this kind of exercise, don't just look at it, write it down. Write down the two possibilities. And from the two symptoms, try to imagine the two potential starting materials. If you look at it, you might think, I understand it. If you write it down, then you have a problem. Remember, at the exam, you have to write it down. There are two possibilities. Three, 4, 4, 5. Let's do a poll. Anyone does? 4,5 is a possibility. If you have 4,5, what can you tell me the starting materials? Because this is what you want to do at the exam. Okay, let's say that you spot one bond that can be broken. Remember that is not broken on retrosynthesis. This is the bond that is going to be formed in synthesis. Don't get confused. But again, separate the charges. If you do 4,5, ideally, I want to think that since this carbon is going to be your delta plus, you're putting the delta minus here. That means you have your role plus aldehyde, and let's call it R, all the rest. So this is the bond you're forming. It is doable, absolutely. There is one problem, which comes from reactivity of heterocycles on the second year. Pyrrole really likes to give polyattacks. It's very, very nucleophilic. So there is always a chance that it carries on. The selectivity at this point is lost. So that's a good point. So you think about it. It's not a bad idea. Technically speaking, it's good. But when you do the synthesis, you might want to say, for instance, I go very low temperature. If you want to keep that very low temperature so that I prevent polyalkylation. That will be the first one. But the second one, technically speaking, is easier. There is a problem of making this compound, which also is doable. Making this aldehyde is also doable with a reaction that I show you in the second year. I don't think you remember. Because I have to be honest, I have to remember as well. So only I did this reaction with the second year 2 weeks ago. But yes, let's take one step at a time. In this case, it's easier. You're preventing the potential polyalkylation. So I'm not using this pyrrole as a nucleophile. You're actually using the other compound as a nucleophile, which is attacking the carbonyl. We always said we keep the carbonyl with positive charge because this is the nature of the carbonyl. It wants to behave as an electrophile. It prefers to behave as an electrophile. For the synthesis in this case, starting on this side, always when you see these diols, you can imagine they are protecting groups. They're like protecting groups of the carbonyls. So whenever you see this one, you connect with a former carbonyl. The retrosynthesis is always going to be something like that. So you have to protect this alpha-beta unsaturated aldehyde. Then you can do HBr, for instance. We are skipping this part because we are focusing on the alcohol, okay? But this is, again, chemistry that you should already know. So you put the carbonyl, then you do the halogenation. You do your Grignard. I ask you something silly, hopefully silly. Why do I want to protect that one before doing the Grignard? What if I do this one first? If I do the halogenation of the double bond here first, it doesn't really matter because actually it will not affect the carbonyl. So I can do that one first, and then I can do the Grignard. But I'm using a protecting group. I keep saying protecting groups are necessary evil sometimes. This is one of the cases. If you do the Grignard from this one with the carbonyl in place, the Grignard will automatically attack itself. Okay. So if you don't do this protection of the carbonyl, and you do this reaction first, if you do the Grignard without the carbonyl protected, the Grignard attacks itself. As soon as it's formed, if a little part forms, remember that nothing happens at the same time. So you gradually form the Grignard and it gradually attacks itself. So you'll end up with a horrible mixture of something you don't want. This is one of the cases in which the protecting group is absolutely necessary. then you do your reaction to form your alcohol. Okay? So again, strategy. This one wasn't a bad idea, but you need to specify. This is one of the cases where, like we were discussing before during the break, if you want to give me specific conditions, I will accept it anyway. But you need very specific. If you tell me, then I mix these two, it's partly, you might get half mark. It's not completely wrong, but it's not completely right. It's not selective. What about this one? Again, 1, 2, 3. Well, let's go to prime. Now we are using the alcohol instead of making the alcohol. Then we will make the alcohol. But when I talk about different groups like alcohols and amines today, we are always talking about both the use and the reactivity of these functional groups and the synthesis of the same functional group. Sometimes you need to use the alcohol, but if you need to use the alcohol, you need to synthesize the alcohol too. So you need to know both. Where do you cut this one? That should be a very easy one. This is an ester group. How do you form esters? What's the easiest way to form esters? Anyone? Fischer esterification, carboxylic acid, may be activated of the alcohol. And again, we are talking about alcohols, so probably you have to put an alcohol somewhere. Okay, let's carry on. Then once you have this kind of molecules at the exam, then it's another game, brand new game completely. So you treat them separately. If this reaction is so easy to do, like Fischer esterification, and none of the conditions that you're going to use in the Fischer esterification are going to affect any part of the molecule, that you take for granted this reaction works. This is definitely, necessarily the first bond that you want to break from the strategic point of view. Let's do B first. How do you do this alcohol? Because we are focusing on the alcohol. How can you make this alcohol? I'm sure you have done it with Marcella, even from the asymmetrical point of view. This is a reaction that is super nice whenever you need to form these alcohols, especially primary alcohols with 1, 2, and 3, where 2 and 3 are both carbons. You did it with Marcella so much. Please, don't disappoint me. No pressure. How can you make this? What do you start with? Because Marcella also uses a lot of stuff. Marcella, I know that she uses a lot of retrosynthesis in the end, because then eventually, again, also from her point of view, if you want to synthesize what she needs, you start from the retrosynthesis and then you do the synthesis. Once you do the synthesis, sometimes this is a reaction that, if it's needed, can be easily done in a stereochemistry control condition. I'll give you a hint. This is carbon number 4. You cut it here. What are the starting materials? If you cut it here, if you don't know how to do it, again, write it down. Here you can have plus here and minus. Again, you don't need to remember any reactions necessarily. You just put the charges. Or you can have minus here and plus here. What is best, A or B? And if you choose either A or B, what are the starting materials, especially this one. If you want to have a plus here, again, keep going with the strategy. Start with the delta minus. If you have a delta minus here, you have a delta plus there. Can you have another delta plus there? The answer in this case is yes. Only one condition, symmetry. How this molecule becomes symmetrical. Oh, you're gonna scream when you say it. I'm sure Marcella uses so much because she likes doing the oxidations, because they are very useful, not because she particularly likes. Do you use an epoxide? Oxygen of a strong delta minus. These one are equally, since there are two carbons that are absolutely equivalent, you cannot distinguish one from the other. They have two small delta pluses. It means that any nucleophile can attack here or the other and ring open. And when you ring open an epoxide, you get a variation. Unless you have, of course, unless this one was not symmetrical, you have R and R prime. This is another case. Now we're focusing on this one. So this reaction really works very well with an epoxide. If you have an epoxide, your epoxide is always your electrophile. The nucleophile is another part of the molecule. Whatever the other part of the molecule is, it could be a nitrogen for an amino group. They make nice amino alcohols using epoxides. Depending on what you have around, it can be, you can do in asymmetrical, as asymmetrical point of view. That is what Marcella really tackles. In my case, normally speaking, I will not ask you. I will not ask you for the stereochemistry. I care more about the strategy. So these are the symptoms. All commercial available, despite the epoxide as it is, the oxirane, the proper one. It's a gas, it's super corrosive. You get it in cylinders, it's a reaction. It's one of those reactions that is easy on the paper. It's not exactly easy in the lab, but it works super well. What about A? We forgot about the A part. Again, I'm mixing different functional groups because every time that we have retrosynthesis, you need to consider different functional groups at the same time. This one can come. This is not part of alcohols or amines, but this is something that you might do easily in this way. What is minus? Where does the minus come from, you think? That's a reaction that my group does properly in the lab. It's a very easy reaction. It's very easy, I mean, very high yields, selective. You just need to form either the Grignard or the organolithium equivalent of this one. And then you bubble CO2, which you don't necessarily need. You can do it with a cylinder, but CO2 is not like an epoxide. It's quite inert compared to it. Just don't open it fully, otherwise you suffocate. But even easier, dry ice evaporates slowly, creates CO2 anhydrous, which if you channel it into and bubble it into a reaction in the presence of a Grignard reagent, gives you the carboxylic acid straight away. Then this one can be connected to an alcohol as well. Because how do you make this one? You need the bromide here to make the Grignard. And the Grignard and then the bromide can come from the alcohol. And in this case, you need to form the alcohol too, because today we're talking about the alcohol. We are focusing on the alcohols. So to form the Grignard, if I tell you that you need to carry on because I gave you one of those as starting materials, you need to get the bromide or the chloride, because the Grignard works with the chloride. We keep using just the bromides, but actually the Grignard works well enough with the chlorides. But if you do, especially in the lab, the bromide is easier. But the bromide must come probably from an alcohol, and then you need to synthesize this alcohol. How can you synthesize this alcohol? Again, easiest way to synthesize alcohol, either here or here, and this alcohol is a former carbonyl. You put a delta plus on this carbon, and you can either put the delta minus here, or the delta minus there. Again, it will be two Grignard reagents, either the aliphatic Grignard or the aromatic Grignard. I would probably go for the aromatic Grignard because it's easier to make in the lab, but the other one is equally good. And again, you're reducing the alcohol and forming the alcohol. I would probably go for this one, but starting here and do the Grignard of the isopropyl, that's commercial. You can buy it in solution already and use it straight away on the. In this case, you need the aldehyde. You don't do. If you're asking on this one, this part might come from the aldehyde, so Benz aldehyde. Don't do the ketone, because the ketone will have one extra carbon. I'm telling you because sometimes I know historically the students don't count the carbons sometimes. Please count the carbons. The synthesis is super easy. You start with this one is commercial, or you can make it. You made it actually in the lab. You saw how easy it is to make the Grignard of this, the bromobenzene. Then you use just your aldehyde, you get pure alcohol. Then, this is from the first year, how to turn an alcohol into the corresponding halogen alkane. Phosphorus bromide, you can use phosphorus chloride. It could be tribromide or trichloride. More likely it's going to be pentabromide or pentachloride, which is stronger. Or another easy one, if you want to put a chloride, for instance, is thionyl chloride, you remember. But it exists the version of the thionyl bromide instead. So if you correlating agent is this one. Thionyl chloride. Horrible things also for composting. Sorry. Super reactive, but not that toxic. It is toxic. It releases, with even traces of moisture, it releases HCl. So it is quite aggressive, but I wish all the compounds were as toxic as this one. There is equivalent of an equivalent of the bromide here. But probably if you want to put the bromide, phosphorus tribromide or phosphorus pentabromide, they will both do. So again, in this case, you are using the alcohol, you are forming the alcohol and using the alcohol. So in all these parts is going to be the activity of the functional group we are talking about and the synthesis of the same functional group, because you need to do both. If you are in the presence of other functional groups, again, think about the order of events. Remember that at some point you also need, if there was an exam, you also need to do A plus B. But A plus B, we saw that at the beginning, it was the esterification. Carboxylic acid on one side, alcohol on the other side. You put drops of any acid, a couple of drops of sulfuric acid, and the esterification goes well. Happy with the alcohols. Before I carry on, questions on the alcohols. Please ask anything, or I will tell you what is actually absolutely crucial on the alcohols. Do you think there are problems when forming alcohols? What do you think is the most common problem when you're forming alcohol if you want to keep it stable? Because that will appear in some exercises. Sometimes it's a good reaction, sometimes it's a sad reaction. Sometimes you want to prevent it. What is the most common problem that I really would like you to keep in mind whenever you're making alcohols? And I'm telling you, it's not the hangover. What is the most common problem of alcohols? Let's say that you have an aromatic, you form an alcohol and you have an aromatic group next to it. One of the most common potential problems of that potentially is also that one. It's not a bad idea, but probably the most common one is the opposite of what you're saying. Dehydration to form a double bond. Sometimes you use alcohols. We will see when we make double bonds. Probably the easiest way to make a double bond is to create the corresponding alcohol first, then cook it or put some acid. If you can eliminate the water molecule, you leave behind the double bond. Sometimes the formation of the double bonds in this way is the easiest. We will see that more carefully when we do formation of double bonds, because there are other ways to form double bonds. Let's say that sometimes it's not that easy to control the reaction of the elimination because it tends to form the most stable double bonds no matter what. So if you want to get a cis, which is the least stable, you need to do something else. But generally speaking, if you have an alcohol, if you form an alcohol in a position where you have anything which is conjugated, it could be carbonized, it could be a double bond, it could be a series of double bonds like a benzyl ring. If you have this alcohol in this position and another, even one proton, protons easier, even one proton, you need to prevent this reaction from happening. It's not that easy sometimes because this one is strongly conjugated with the aromatic ring. So sometimes you really want to prevent it. So let's say that you do this reaction to form the alcohol in that position. You start here. And then on the other side of the molecule, you say, yeah, I need to use a strong acid. I say, hold on. If you use a strong acid, you might eliminate as well. So you don't want to do that. Maybe you invert the order of reaction. You do something which requires strong acidic conditions before. Who knows? That's your choice. Another thing that I would like to remind you from when you need to form the alcohol, when you do synthesis, and you use basic conditions, always tell me I need to put an extra molecule. Sometimes even water. You quench a Grignard reagent that formed an alcohol, even just with water, and that will do. The water gives you enough protons, and the Grignard and the compounds that comes from the Grignard is so basic that it takes easily a proton from water. Or mild acidic conditions, that will do with me. Maybe don't kill it with sulfuric acid, but amino groups. There are so many different, I don't want to exaggerate. There are different ways to form amino groups. It's very important that we distinguish from the strategic point of view. It's very important that we distinguish now if you are forming aliphatic amines or if you are forming aromatic amines. We will do in a different way. Strategically speaking, you always want to do in a different way. If you want to do aliphatic amines, this is not the easiest reaction I will start with. But if you remember that and you can do that in the lab, if you do that on the paper, let's do it. Want to do it in the lab? I will try something else. This year, we just got the Nobel Prize for click chemistry. This reaction works very well for click chemistry. But if you want just to form amines, there are probably easier ways. Remember that whatever the retrosynthesis is, if you decide to go for this one, the azide, which could be sodium azide, which is extremely explosive. Remember, there is something like that. sodium plus. If you have N minus here, you have this one plus, and you have another one pair there. This compound is unstable. It's definitely unstable. But it's doable. So if you want to do that, you have a long halogenal alkene chain. You take the sodium azide carefully. You don't isolate the corresponding azide. And you get your amino group in very high yields. So this is something that you can do. I will say that this will be my last option. You must have a very good excuse if you want to do that. If you want to, I say you don't isolate the corresponding azide because it's as unstable and as explosive as the starting one. Then you treat it with a strong reducing agent and you saturate it completely. Then the amino group is super stable. That is not a problem anymore. That's why you don't isolate it. You do everything in situ. Reduction of nitriles is probably an easier one. One thing you really want to remember when you do reduction of nitriles, you always write the nitrile as it is, CN. Remember the presence of this carbon. I've seen so many times students miscounting the carbons because they thought, okay, this one is not that, no, it is that. If you reduce this one, you're creating, this is a triple bond carbon nitrogen. You want to end up with a single bond, but the carbon still, this carbon will still be this one. So count the carbons. But I'm not going to ask you the mechanism. I'm not going to ask you the mechanism of any reactions at the retrosynthesis exam. If you know it, and if you want to do it on the paper, please do it. It's not going to be a problem, even if it's wrong. I won't count it. But you just need to remember that how to make the cyano group as well. Another typical case of, yeah, this is toxic. Cyanide are not toxic. Although I did it often in my research, if you use copper cyanide instead of potassium or sodium cyanide, don't take it as a dare, but copper cyanide, you can even ingest copper cyanide without killing yourself, unless you do, you do a lot. If you have a full meal with potassium, with copper cyanide, yes, you will kill yourself. I don't see why. There are easier ways also for doing that because it's going to be painful. But potassium cyanide is something that you can use easily on the paper, or sodium cyanide. Super toxic in the lab. You need to call, in my former lab, when I was in Edinburgh, we needed basically to have the ambulance on call whenever people needed to use potassium cyanide, just in case. And we had all the breathing apparatus next to us. Also, I used that also when we used copper cyanide, but that was overkilling because I knew the copper cyanide wasn't that extremely toxic. Only I did know the other people from health and safety not necessarily know. The cyanide, they say panic, panic, panic. But this is a very nice reaction that you want to use. So if you need to create an aliphatic amine, you can think about something from the cyanide, but then there is a huge chance that you might need to tell me in the rest of the molecule, how do you put the cyanide group? The cyanide group normally it does SN2 between these two. So you start from the corresponding bromide. Again, chest 1, 2, 3, 4. You start from I want the amine. You need to, if you want to use the nitride, you need to think about, yeah, I need to come back to the bromide. So start doing all the different steps all at once. This reaction it's a very nice one. What do you use to reduce the nitride to the aldehyde? This is a question you want to check on the Claydon again. This is a very, very particular reaction to form the aldehyde. Let's go for this one. probably the easiest way to do amination, to create amino groups. You hopefully remember from, I don't know if Jules did it. I definitely mentioned it in the first year. I think I mentioned it in the second. I'm pretty sure Jules did it at some point. And most likely also Marcella used it. I'm sure Marcella used this reaction because it's the easiest way to create amino groups in a nice and selective way. All organic people, let's say. Not that difficult in this department because it's only me, Joel, and Marcella. But we all use this one, and we always like this one. So when you have carbon heteroatom bonds, you normally want, this is a very good point to start your retrosynthesis. If you have different possibilities, you choose what you think is best. Well, 5 minutes left-ish, but all the rest is going to be easy. I only want to be sure that we mention the aromatic ones. So, if you cut from the carbon-nitrogen bond of the carbonate, it's a formation of the amide. The amide is very easy. This is what proteins do. It's a very easy reaction. So definitely is the best starting point of your synthesis. But then you go back to the amino groups. And you have from this one different possibilities. You can have double bond here, you can have double bond there, and you can start from another amide. Because remember, there is always a chance carbonyl off, carbonyl on. Always. It's always a chance. In all the different cases, you want to cut again the carbon-nitrogen bond because this is the weak bond. Carbon-carbon bonds are far more difficult to cut than carbon-nitrogen, in this case, carbon heteroatoms bond. In both cases, here in an amide, only the double bond is on a different position, so the two starting materials are also different, but the group is the same. Because in both cases, you can do the reaction that is the most common to produce amino groups. Remember the name? I'm sure you use it with Marcella. Marcella used it. Probably the easiest, the most common way to produce amino groups is reductive amination. You start from the equivalent of the carbonyl, you dehydrate, and then you need to reduce down. If you form the amine is stable, easy to isolate, stable on the bench. If you want to get the corresponding amino group, you need to reduce it down. All these parts, if you want to do from the synthesis, from the strategy point of view, all of those are plausible. All of those. Again, that depends on what's on the other side of the molecule. Depending on what's on the other side of the molecule, you choose one over the other. Or sometimes they're interchangeable no matter what. In this case, it's easier for you because you have plenty of choice. But in all cases, in all these cases, you need to do reductive amination at some point. So, for instance, we choose this one, aldehyde, an amino group. You do to prepare the substituted amino group. You isolate this one. You can isolate, or you could do that in situ. On the reductive amination, you could do everything in one pot. But this one can be isolated. So not necessarily has to be done in situ. And then you use reagents. Whatever a reducing agent can be good for a reductive amination. Probably the most common one you might want to remember is a milder compared to others reducing agent, and is a sodium cyanoborohydride. I am pretty sure that Joel did it and Marcella did it as well. I'm pretty sure that both of them use sodium cyanoborohydride. But again, if you tell me sodium borohydride, it will do. Maybe it's overkilling, but it will do. You need to be careful because sodium borohydride can reduce other parts of the molecule. Sodium cyanoborohydride is a lot milder. The fact it looks similar, it's a lot milder the sodium borate, right? And you might reduce specifically just that part of the amino group. So you form selectively just your reductive amination without affecting any other part of the molecule. Instead, if you use sodium borate and there is a group that might be another carbonyl on one side that might be reduced, you might get into regioselectivity problems. So you have isomers. This one, I want to be sure that I do everything. So I will give you this one very quickly. Reuse the slides and do it at home. Again, in this case, I'm using both alcohols and amines to do that. So in this case, on our epoxide, whenever you see two carbons next to each other and they are completely saturated, think about you might do that using an epoxide. And this is what I really want to do for sure. The amino groups into aromatic rings are normally done by nitration or reduction of the amino group. There are not many other ways to do that. So if you see an aniline, even a substituted aniline, there is another way that we saw that on my first part of the course. There is another way to do substituted anilines, but the most common way is you introduce in retrosynthesis. In this way, from the synthesis point of view, remember that you need to determine where the nitrogen is. That depends on the other substituents around. But normally speaking, whenever you do amination of the amino group of the aromatic group, is you place a nitro and you reduce all the nitro on this one. Again, be careful because there are parts that maybe be reduced in the same moment, and you really want to choose the sequence of events. Do this one at home. This is a review problem. We have three potential places where to attack, where to start your retrosynthesis. You need to tell me where you want to start disconnecting. I think I will leave it here because if you do this one at home, unless you really want to do this one now. How does it look like? Again, quick recap on the amination, because we were discussing on the before even starting. Do you need to remember all these conditions? It would be good if you do remember, at least roughly the conditions. But aminations, if it's aliphatic, reductive amination. If it's aromatic, most likely it's going to be nitration of an aromatic group and reduction of the amino group. Reduction of the amino group, hydrogen with palladium over carbon will always do to it. I do that massively in my research group. I normally do reaction with hydrazines that we probably saw with Marcella, just because hydrazine is a good reagent that creates hydrogen in situ. Or I do reaction with some Lewis acids, for instance, tin chloride, that works well. But that is for the aromatic groups. The only other one which creates automatically substituted anilines, starting from, let's say, a bromobenzene derivative. If you remember the first part with me, I did the Buchwald-Hartwig reaction. It's a cross-coupling reaction, which you might start with an amino group already formed, which is going to be your substituted aniline, your equivalent of the bromobenzene derivative, and palladium or complexes of palladium as a catalyst. You know, one of those cross couplings called Buchwald-Hartwig is very selective, and you can do substituted amines in a way that is otherwise very difficult. Okay, I think I will stop here, and I will not give you the solution with one straight away. Please do it at home.